Welcome to EDU World Space.
Okay, so problem 12 in chapter 13 is a two-part question. Part A is asking us, what is the acceleration due to gravity on the surface of Venus? And we're told two things to help us figure this out. We're told that the mass of Venus is equal to 81.5% the mass of Earth, and that the radius of Venus is equal to 94.9% of the radius of Earth. So how do we figure out the acceleration due to gravity on different planets? We know that on Earth, it's just equal to g. So the acceleration due to gravity on Earth, well, it's just a constant. We know what it is. Um, but how do we actually derive this? How do we get here? So what we do is we take Newton's second law, and we imagine that we have some object in free fall and that it's not experiencing air friction or anything. So for an object in free fall with no other forces, we're just going to see that the sum of the forces is the force of gravity is equal to mass times acceleration. So the next thing we do is we take the universal law of gravitation, which says that the force of gravity between two objects is g times m1 times m2 divided by the radius between those two objects. And what we do is we make mass 1 the mass of Earth, and we take mass 2, and it's the mass of whatever falling object is. Or it's the mass of whatever that falling object is. And we're just going to leave it as an m, where this is the radius of Earth. And then what we do is we set this right here equal to that, since they're the same thing. So we're going to get that g me times m divided by re squared is equal to ma. And we can see the masses cancel, so it doesn't actually matter how heavy the falling thing is. The acceleration it experiences is constant. So here we see that this reduces down to g me divided by re squared equals a. And this a, well, this is just g, or g sub e. It's the same thing. So in order to find the acceleration due to gravity on Venus, we're going to repeat the same process, but now we're going to have g mv divided by rv squared is equal to, um, let's see, acceleration due to gravity on Venus. Okay, so we just take what we have now and we plug in the numbers it gives us. So we know that the mass of Venus is equal to 81.5% the mass of Earth. And we know that the radius of Venus is equal to 94.9% the radius of Earth. Is equal to AGV. So if we actually divide those out, we're going to get that this is 0.9. Sorry, it's 90.5% times g times the mass of Earth divided by the radius of Earth squared. And this is equal to AGV. So it kind of looks like we're stuck because we don't know what the mass of Earth is or what the radius of Earth is. We just know what it is in relation to Venus, which we also don't know exactly. But again, if we just look at what we've already done, we know that this quantity, g times me times re, well, that's just equal to the acceleration due to gravity on Earth. So that means that if we just take this a step further, we have that the acceleration due to gravity on the surface of Venus is equal to 90.5% the acceleration due to gravity on Earth. So now part B is asking us if we have a 75 Newton rock on Earth, what will it weigh on Venus? So if we write out Newton's second law for this object on Earth, then we know that 75 newtons is going to be equal to the mass of that item times the acceleration due to gravity. So we don't know this m, but we can solve for it real quickly. So we just take 75 divided by g is equal to m. And if you divide that out, m is equal to about, let's see, 7.65 kilograms. So then, if you do Newton's second law for the same object on Venus, then we have the force of gravity on Venus is equal to the mass of the object times the acceleration due to gravity on Venus. So we don't know what this is, but we just solved for this, and we just found what that is a second ago. So that means that all we got to do is take our numbers and plug them in. So we're going to get that the mass multiplied by 90.5% times the acceleration due to gravity, which is just 9.8. We're going to get that the object weighs approximately 67.9 newtons